Hi guys, in this video now what we'll try to do is we'll try to answer the last two questions. I think we'll do this together. Now you guys will have to be very careful with the previous calculation. At this point I'm rushing with time, so I'm really not going through my methods, so I might mix things up here. So let's see, to determine if the wedge is in self-lock or not, and then also to determine the value of P needed to make the wedge the wedge lock, what are you going to do here? So we're going to go back to the free body diagram that we drew for the previous calculation, just for the wedge there. So this is what we had. Now, of course, we did have what that F was. So F was 0.29 NC. So this was equals to 0.29 NC. But this time around, we're going to try to find a force P that is in the X. And let's try to say this force is needed to keep the pin or the wedge in position. Let's try to do things together. Now, if we end up finding P to be 0, it means that the wedge has self-lock. But if we find P to be non-zero, it means that the wedge doesn't have self-lock. And the value that we're going to find here will be the value of the force needed to actually make sure that the wedge is locked there. Now, how do we do that? So we already summed forces in the y-axis and we saw what we got from there. Now we're just going to sum forces in the x-axis and equate to 0. So if we sum forces in the x-axis, we have that 180 cos theta there. So it is going to be 180 cos theta. That is in the negative direction, so I'll put a minus there. Then I have P itself. Our theta is, don't forget, that is 30, the wedge angle. And then we have P here is backwards, so it is going to be minus P. And then what else do we have? And we have the force of friction at the bottom. So it is going to be minus 0.29 NC. And yeah, basically this is everything. Let's take our force P here. Let's look at it as the force needed to pull the wedge out. Let's do it like this, so at least we have a positive force here. Okay, so this is everything. I count 1, 2, 3 forces. Yeah, that's everything. So this is equals to 0. So from here, all we have to do is work this out for P. So in the end, everything else goes the other side. We have 180 cos 30, and then we have plus 0.29 NC. Then this will have to be just that. Okay, so here I've just noticed that in the previous calculation, I actually did leave out the normal force coming from the normal force NB. So NB, of course, you have to see that NB will be acting vertically downwards like this, coming onto the wedge. So you have to factor it in the other calculation as well. It will have two components. NB in the x-axis will be something like this. NB in the x-axis will be this. Our angle is 30 degrees. So NB in the x is going to be NB itself. And then the angle you're going to use for in the x-axis is going to be sine 30. And then NB in the y-axis, the one that you were supposed to add in the previous calculation, NB in the y is going to be NB, and then this is going to be cos 30. So please try to make those adjustments. So perhaps I might do that. Yeah, let me actually just do that as well. So yeah, this is what we did in the previous calculation to find NB. To find the frictional force. Yeah, that is what we did. So let's just redo this very quickly. Okay, so when you sum forces in the y-axis, what are you going to get there? So if you sum forces in the y-axis, you see that you have 3 forces in the y-axis, not the 2 that we had. So going up, you have NC. And then going down, you're going to have that NB cos 30. So you have NB cos 30. Then you have minus, that is going to be 180 sine 30. And then these are the only ones, equals to 0. So from here you have NC being equals to just this. NB, we did have what NB was. NB was 920.675. So NB was 920.675, 920.675. And then we have cos 30, then minus 180 sine 30, And if we do this, we get 920.675 cos 30. Yeah, when the other side, this is also going to be plus, so that is plus, let's just do this. Okay, here we get 887.3233 kilonewtons. So this is what you multiply with your force of, with your mu there. So multiplying 0.29, multiplying 0.29, this is what gives you the force of friction at the bottom as 257.33 kilonewtons. Okay, so having done that, now we come to this part. So we're still saying that here we still have the normal NB in the y-axis and NB in the x-axis. So NB in the x, where was my NB in the x pointing? Okay, NB in the x was pointing to the right, so something like this. This was NB sine 30. So now I'm summing forces in the x-axis, and let's see what we have here. So we have P to the right, and then what else? We have NB sine 30 to the right as well. So we have plus NB sine 30 to the right. Then we have minus the force of friction 0.29 NC to the left, and then we have that 180. Yeah, that's 180 cos 30 also to the left. So we have minus 180 cos 30 to the left. That's everything equals to 0. 1, 2, 3, 4. Okay. From here we have P is equals to, this becomes 180 cos 30 plus 0.29 NC minus NB sine 30. So this is giving us, in this case, minus 47.13 kilonewtons. So you guys have to go through this. I'm doing this a little bit fast. There's a high chance I've made mistakes here. So in this case, it means that this is actually not in self-lock, and we need this force for this to actually be in self-lock.